Hello everyone. In this session and the following sessions to come, we're looking at solving an image classification problem using a multi-layer perceptron model. We are going to make use of this particular dataset called Fashion MNIST. As the name itself suggests, we have this large collection of images which are your fashion related images or fashion clothing and apparel related images. So first, before we begin understanding more about the data, let's look at who has created this particular dataset and what is their primary intent behind creating this. So there's a particular organization called Zalando. So this is a large e-commerce platform, a fashion e-commerce brand within Germany. So this is spread across various countries. So this is a multinational brand, and this is a small entity within this particular organization called Zalando Research, who have created this particular dataset called Fashion MNIST with a primary intention of replacing the original MNIST handwritten digit data for evaluating any of the ML algorithms that the researchers create. So what is the primary purpose of MNIST datasets? Researchers across the various organizations tend to make use of MNIST dataset in order to benchmark the different ML algorithms that they are creating. They'll also use these datasets to rapidly prototype any of the algorithms that they design newly. So these are the primary two reasons on why researchers tend to use this MNIST dataset quite a lot. Fashion MNIST dataset, on contrary to your MNIST dataset, generally provides much more complexity during the training process. So MNIST handwritten digit data is very easy and it's overused currently because every researcher across the organization basically are trying to prototype their algorithms based on this particular data. And it is said that if the algorithm is not working on MNIST dataset, it's said that doesn't work on any other datasets as well. So that's the primary intuition behind it. And MNIST dataset cannot represent better on modern computer vision tasks. So these are the primary reasons on why the creators have come up with this new dataset called Fashion MNIST dataset. The structure of this particular data, that every image is now represented in the form of 28 by 28 pixels, exactly matching with what is represented in the digits data. Similarly, we only have 10 different labels, which again is matching with your original number of labels that you had in MNIST handwritten digits data. So they try to maintain the same structure so that any algorithms that are already built on MNIST handwritten digits can easily be recreated or retrained using this new dataset here. Okay. So the primary reason on why we are considering this particular dataset is for us to get well versed with all of these data science and machine learning concepts. Let's say that you would want to implement batch normalization and also look at implementing the dropout regularization in order to create a generalized model that performs well on different sets of unseen data. So this is your task. And in order to learn this properly, MNIST datasets are very much appropriate. Not necessarily these concepts. Could be any other ML or deep learning concepts. It's better understood with the help of these datasets. So this is a primary reason on why we are considering these datasets. Moving forward, we'll consider other sets of problems and try and solve them. Okay. It's not that we are confined to only this particular dataset. You can explore more on this particular GitHub page. Try and understand what are the different descriptions that you can find for a particular target variable. So the target variable clearly is multi-class in nature. So there are 10 different labels associated. So each of these particular label has got a description again. So t-shirt is associated with label 0, trouser with 1, pullover with 2, so on and so forth till ankle boot with 9. Okay. So you can actually load this particular dataset with existing Python built-ins. So you need not externally download the complete data and try to read the complete data image by image. It's not necessary to do that. So there's a particular package called Torch Vision, which we are going to leverage in order to import this necessary class called Fashion MNIST, which is going to help us load the given dataset. The primary step or the very first step that we are going to take here is to create the dataset and DataLoader objects. So dataset and DataLoader objects are going to help us read the given data, read the XY data batch by batch. Where while creating the DataLoader object, you will define what could be the batch size. All of this we already have implemented in our previous sessions. However, we are now going to read this particular Fashion MNIST dataset, create dataset and DataLoader objects respectively. Also try and understand if the image data that you are trying to read basically is represented in the form of tensors or not, whether it's normalized or not. So data normalization is another key step that we are supposed to look at. Let's move on to this particular coding exercise. Here we have this particular fashion MNIST image classification problem that we are trying to solve now. So we have imported all the necessary libraries and modules. I've also turned off all the warnings so that whatever output that we are trying to observe is more legible. So I have tried to mount the Google Drive as well so that I can access whatever subdirectories that I'm having within my Drive folder here. The very first step that I'm going to incorporate or implement here is to read this particular MNIST data by using this class called fashion MNIST. So within this particular parenthesis, I'm now going to provide the root directory into which I'm supposed to download my data. So root is equal to data. So I'm providing the subdirectory into which I'm planning to download the data. So I'm setting download is equal to true. So as to indicate that I want to download all the image files here. So while downloading, I also would want to transform the existing image data into tensor objects. So I can make use of this particular module called transforms here, which again is imported from Torch Vision package. So transforms.toTensor is going to help us convert this image data into tensor objects. So now I have converted this into tensor objects here. Cool. So whatever statement that I have written here on right hand side, I'm assigning to a new object called dataset. So this is nothing but it's an instance of this particular class called fashion MNIST. We clearly know about all of that. I also would want to create complete dataset by making use of the same class again. But this time around, I'm not trying to download anything, but I am necessarily going to create a dataset object specific to train set alone. Okay, let me copy this root directory as well. And I'm not providing any parameter called download. Instead of that, I'm providing train is equal to true. So as to indicate that I am trying to create a dataset object pertinent to the train data. So let me write a comment stating that this is going to be train dataset, or I can mention it as complete train dataset. I can also include an additional comment here stating that we are creating dataset objects now. Okay, cool. And again, I would want to transform this image data into tensor object. So I will also provide this particular additional argument. Once I complete this activity, I also would want to create a dataset object for test dataset as well. So setting train is equal to false is going to enable me to create a dataset object pertinent to the test set alone. Okay. So you can verify the length of each one of these. So you can look at the length of this complete dataset. It's the number of observations here, number of observations in the test dataset as well. So we clearly know that there are 60,000 different observations belonging to the complete data, complete train data, and there are 10,000 different observations that belong to test dataset here. So whatever train data that I have or whatever complete dataset that I have, I am now breaking this down into train and validation. So this here is going to be my train set. So this here is complete dataset. Complete dataset had 60,000 different records, 60K records. So I'm allocating a major proportion of it to train set. Probably like 50,000 observations I'm allocating to train set, and 10K observations I'm allocating to validation set. I already have this additional data set called test set. So this test set has how many number of observations? This test set already has 10K different observations. So my whole plan here is to create 3 different data sets, one of which could be train data set, which is for the model training process. So validation data set is purely used for hyperparameter tuning. I would want to find which of the combinations of hyperparameters that are present in my hyperparameter grid are more appropriate, or which of the combinations of hyperparameters are producing consistent results when it comes to train loss and validation loss that you are going to compute. Okay, so test set is left completely as unseen data. If you would want to extract an unbiased estimate of how good of a model that you have created, then you are not using test set for any of the training process. So you are leaving test set completely as unseen data. You're not touching it already, right? You're only making use of train set for model training process, validation set in the model training process, especially for hyperparameter tuning in order to find the right values for your hyperparameters. And finally, apply your model object onto the test set. Whatever model object that you create, you are going to apply it onto the test set try and perceive what the loss is or what the accuracy is. Try and compare the loss and accuracy that you have computed on validation set. If there is no deviation that you are observing, then whatever model that you have created is set to produce consistent performance on any given set. Okay, so this is purely to get an unbiased estimate of how good of a model is being performed. Okay, so since we have looked at creating the dataset objects already, now I am going to consider this complete DS and split this particular data into train and test datasets like we have discussed now. I'm going to make use of this random split function, which is imported from torch.utils.data. Okay, so random split, within random split, I am here providing the complete DS that we already have written within the parenthesis. Also providing the number of observations or proportion of observations that should be belonging to train set as well as validation set. Either I can provide proportions like I have provided now, or you can also specify the number of observations that you are planning to allocate to both train and validation sets here. So I'm planning to allocate 50k observations to train set and 10,000 observations to your validation set. Let me call them as train DS and valid DS, which is validation dataset. So length of train underscore DS, length of validation dataset is going to produce the number of observations that are present in each of these datasets here. So we have essentially created all the dataset objects. We have splitted this particular complete dataset into train set and validation set. Now you have train set, validation set, as well as test set here. We have all the three datasets that are required for conducting this model training process now. So the next step here is going to be creating the DataLoader objects. So we are going to make use of these DataLoader objects in order to iterate over batches of your input data. So whatever large number of observations that you have within your input data, we are going to iterate over all of the input data by batches. We are defining a definitive batch size here while creating the DataLoader object. So let me create something called train loader using this class called DataLoader class. Okay. So within the parentheses, I am trying to provide the respective dataset object that I already created in the previous step. Along with that, I'm specifying what my batch size is here. So batch size is a hyperparameter that we can look at tuning further. But for now, I have provided an arbitrary batch size of 128. So similarly, you can create a validation loader as well, which I'm calling it as valid loader, making use of valid DS batch size. Again, I'm retaining as 128. Let me also create a test loader object, provide test dataset object within this parenthesis here. Now you have created all the data loader objects associated with three different sets, train, validation, as well as test sets. Cool. We have never inspected how the data was looking, right? So we essentially have read the image data and tried to convert them into tensor objects straight away when you created the dataset object itself. But you have never tried to look at inspecting any of its elements. Now let's try to inspect what this 0th index would hold. So this 0th index will hold X and Y data. So let me unpack X and Y data here clearly. So my X data here is going to be a tensor object. You can see this is a tensor object. My Y data here is a label. This label can range anywhere from 0 to 9 as we have observed in the GitHub page earlier. Okay. So let me check the shape of this particular X data now. So what could be the shape of this particular X data here? The shape of X data is 1 by 28 by 28. So this is a three-dimensional tensor object, clearly, right? So we always thought that these grayscale images are generally represented in two-dimensional tensors. But for any of the given observations or for any of the images that are present within the datasets, you always have one for this particular dimension. So this represents channel here. This represents height and the width respectively. So this is a 28 by 28 pixel image. The height and width of this particular image is 28 pixel by 28 pixel. However, the channel that you are observing here is encoded with 1. So when it's an RGB image, when it's a color image, the value here is going to be 3. 3 by width, height by width, whatever it is, right? There could also be 4 different channels, especially when you are introducing the alpha transparency level as well. So then you will find a value of 4 for channel. Effectively, you have the associated height and width as well. I believe that you have understood the whole process here. So you need not explicitly provide an additional dimension in case of grayscale images. You can reshape this particular X data into a two-dimensional tensor. Because for each and every image, you'll have this channel value always depicted as 1. There's no point in it. So now I'm reshaping it to 28 by 28. So whatever data that I have reshaped, I've reshaped it into 28 by 28 two-dimensional tensor object now. Let me try to understand what this image is all about. I can simply go about importing matplotlib.pyplot, provide an alias to it. plt.imshow is a function that I can make use of in order to present this particular data in the form of a plot here. I can also provide a CMap stating that it should be a grayscale image. Let's also look at printing this result. So this here looks like a hoodie to me. This looks like a t-shirt or a hoodie, which I'm currently not able to perceive since the resolution is not that high. All the images resolution is very less. You only observe 28 pixel and 28 pixel on height and width respectively, right? So whatever it is, you are now able to understand or perceive the information that's being stored in the form of tensors here. I can also inspect other indices or other values for indices. So this should be X, right? This should be unpacked into X and Y. So let me use X here and reference index position 1. This is an ankle boot. The label associated with this should preferably be 9. It's 9 here. I was so sure about the label basically because I've gone through this particular tabular column where ankle boot is associated with this particular label called 9. Okay. So we have now looked at creating the dataset object and the DataLoader objects as well. And we have tried to read the image data and convert them into tensor objects. And finally, we also can understand how we can leverage this particular DataLoader object and try to iterate over this particular dataset batch by batch. So I'll now consider this particular train loader and iterate over this particular DataLoader object, right? And try to perceive what this particular data is all about. So you can always print the pair of X and Y that you're observing. I'll just try to break out of this particular loop after printing or after iterating for once. Okay. X here is clearly a 4-dimensional tensor object. So X dot shape here is going to be a 4-dimensional tensor object. Here there's an additional dimension. This represents batch size. We're now referencing the DataLoader object. We are not looking at accessing the data directly by using dataset object here. So we are making use of DataLoader object where we have specifically mentioned what could be the batch size, right? So the very first dimension here is going to be the batch size. This here is going to be channel. And this is height and this is width. I believe you are now understanding what each of these values within X dot shape would represent. Okay. So there are 128 different images that are being now read as tensor object here. Finally, you also observe that there is a particular tensor object which stores all the Y labels for the first 128 observations that we have read using this particular train loader object. Okay, cool. So now we are going to make use of these data loader objects that we have created and try and iterate over this particular data set and try and establish a particular training process now. And finally looking at finding the right values for your model parameters, that is weights and biases. We'll first define how the neural network architecture is going to look like. First define a custom model class and then further look at implementing the training process as a whole in our next sessions to come. Okay, so that's all in this particular session and thanks for watching.